So in this second part of the lesson, we'll now explore how we apply this calculus idea to these three different examples. And as with most things that we do, the calculus that we just worked through in theory will start to make a lot more sense as we apply it to these different scenarios. Okay, so reading question 1, we have a ball that's thrown with an initial speed. So it's giving us our initial velocity of 40 meters per second. That information is currently not on the diagram, so we can go and write that we know that the initial speed v is 40. We are told this time that it's thrown with an angle of inclination, or the angle of projection, of 30 degrees, and that is on our diagram for us. And it's thrown not from the ground, but this time from the top of a stand that is 25 meters above the ground. And we can also see that that information has been listed on the diagram too. So the origin of our Cartesian plane is sitting at the point where the object or the ball is thrown, and then the ground level is 25 meters below that. So before we go reading through the rest of the questions, because there are quite a few questions that they're asking us now to consider, it is a good idea to start writing out these initial conditions that we've been given. So if the ball is being thrown from the origin, from its starting point, then that means that our initial displacement horizontally is 0 and our initial displacement vertically is also 0. We've been told that the initial velocity is equal to 40 meters per second. And as we saw in the previous video, we do need to split that into its horizontal velocity, which will come from the value of that velocity multiplied by cos of the angle of projection. So just taking the horizontal component of it. And cos of 30 degrees is a nice exact value of root over 2, so that also simplifies to a nice exact value for us. And we also need to consider the vertical velocity by taking that 40 and splitting it into its vertical component. Again, sine is a nice exact value of 1/2, so we can simplify that answer too. Now the first question, part A, is asking us to use the top of the stand as the origin, which we've done, and to consider, in this case, acceleration due to gravity being equal to -10. So they're asking us to consider rounded whole numbers here. And they want us to firstly find the equations for the horizontal and vertical displacement of that ball. So that means that we need to find the equations for x, or the horizontal displacement at any point in time, and we need to find the vertical displacement y at any point in time as well. Now these initial conditions that we've written down are the values when time is equal to 0. And what we want to do now is find two separate equations for any point in time. So it means that we need to start at some known equations for the movement of this ball with respect to any point in time. Those two known equations come from considering the force of acceleration that is acting horizontally and vertically against this ball, as that's the known information that's given to us. So horizontally, there is no force of acceleration acting on this particle. So we say the horizontal acceleration is 0. And vertically, we've been told to use this value of -10 to describe gravity. So the vertical acceleration acting on the particle is at -10. And the second step we are going to now do, they are both derivatives of our velocity. So we rewrite them as the derivatives, and then we integrate both of these to find the horizontal velocity and the vertical velocity. So integrating 0, we get just a constant value that we will now use our initial conditions to find. And integrating -10 with respect to t means that we now have -10t plus some unknown constant value that again we'll use the initial conditions to find. So initially when t is equal to 0, our horizontal velocity is equal to 20√3. So making that substitution into the horizontal velocity equation over here, we get our constant value equal to 20√3, and so we have our equation horizontally for the velocity. And now we need to do the same thing for the vertical component. So when t is equal to 0, our vertical velocity was equal to 20. So making the substitution, we obtain the c value of 20, and that gives us our equation vertically for the velocity. Now we were asked for the displacement, so we'll do the same process again. We'll start by writing both the velocity terms out as their derivatives. We'll then integrate both sides of these equations, giving us, when we integrate dx with respect to dt, x is equal to 20√3t plus a constant value. And for dy on dt, we'll obtain y is equal to minus 10t squared over 2 plus 20t plus a constant value. And now using the initial conditions again, we will evaluate our values of c and we'll be at our answer. So when t is equal to 0, both x and y are equal to 0 because the ball was starting at the origin. So making the substitution for t, x and y, we get that c will equal 0 for both equations, leaving us with our horizontal displacement and simplifying our vertical displacement. And that's the answer to question A. Question B now asks us to find the maximum height of the ball and the time at which that maximum height occurs. So remember that when you see this word maximum, it's linking to that first derivative, or in our case, the velocity when it's equal to 0. So we're looking for where that stationary point is occurring on the curve. Now, because we only want the height, we are also only concerned with that vertical rise. So that means that we only need to consider the vertical component of our velocity to find the maximum height. And the equation for that we obtained when we were working part A. So we'll take that vertical velocity equation and set it equal to 0. And you can see that as we now solve this equation, it's finding the time at which that vertical height is occurring. So now that we've found this time, we can substitute that value back into our equation that we obtained for the vertical displacement of this ball. And now substituting that value of 2 into the equation, we get that the maximum height is 20 meters. So that's 20 meters above the stand. For question C, we now want to know what is the ball's speed at that maximum height. So this is now asking us for the magnitude of the resultant velocity at this maximum height that we just obtained. So remembering that the resultant velocity is coming from the combination of our horizontal velocity and our vertical velocity. Now remembering that we have already used this vertical velocity to calculate where this maximum height was occurring in question B. And so we know that this maximum height is occurring when our vertical velocity was equal to 0, which means that this vertical component of the velocity we already know the value of, and we can substitute that it is equal to 0. So now all we need is the value for the horizontal component of our velocity at this particular point in time. And this we calculated as we were doing the calculus in part A, and we were finding that horizontal equation of displacement. So we ended up through that calculus obtaining that at any point in time, the horizontal velocity is given by the equation 20 root 3. So we can substitute this working that we have from part A into our expression. And we've got that the speed at that point in time is 20 root 3 meters per second based on the units used in the question. So you can see that once we've done the calculus part of these questions, the subsequent questions after that are very application problem solving type questions. So they are asking us to now explore different parts of this particle or this object's motion and use the information that we've been given in the scenario to find different sections of that motion at different points in time. So it is vitally important that you are breaking these questions down very carefully and identifying exactly where and what this question is asking you to consider. Okay, so moving on to question D now. It's now asking us to find how far from the stand the ball is at its maximum height. So now it is asking us to find this horizontal distance from the base of where the stand is to where that maximum height was achieved. So that means we are now being asked to consider only the horizontal displacement of the ball, which we obtained the equation for when we were working part A. And we want to know that horizontal displacement at time equal to 2 seconds, as that's the time when the maximum height occurred. And a simple substitution of that t value of 2 gives us that the ball is 40 root 3 meters horizontally from the stand. And we're best to leave our answer in exact form unless we're asked to round to a specific number of decimal places. The last parts for this question, question E and F, are a little bit more involved than the last two. So for question E, we are now being asked to calculate the time of flight. So that is asking us to calculate the t value at this end point where the ball has hit the ground. And secondly, what is that horizontal range of the ball's motion? So it wants to know what is this total horizontal distance or displacement of the ball. Okay, so we can see from the diagram and also from reading the scenario in the question part above that the end of the ball's motion is occurring as it hits the ground 25 meters below the stand. So we can make this statement that the end of the ball's motion is occurring when that vertical displacement is equal to negative 25. And that means that I can now make the substitution of that negative 25 into the vertical displacement formula that we calculated as we were working out question A. And you'll see that this now gives us a quadratic equation. So whenever we're now looking to solve a quadratic equation, we're going to bring everything to the left-hand side. You'll see that it has a common factor of 5, and I hate working with negatives, so I'm going to take the negative 5 out. And then because our equation is equal to 0, we can just divide that -5 from both sides, and we end up with a much nicer quadratic equation that I am able to factorize. And then looking at the two solutions that we get from this, we're going to dismiss this -1, as we know that we can't have negative time. And so we can see that the ball is going to hit the ground at t is equal to 5 seconds, since we can't have t being equal to -1. So this finds for us that the time of flight of the ball is a total of 5 seconds, and we can make that statement to answer the first part of this question. And now we want to use that time to calculate the total horizontal displacement from the origin, where the x value would be 0, all the way up to the x value that occurs when t is now equal to 5. And so now making a substitution for that t value into our horizontal displacement formula, we get that the horizontal range of motion is 100√3 meters. The last part of this question is now asking us to calculate the impact speed and the angle at which the ball is hitting the ground. So remembering that speed is the magnitude of our velocity, it's now asking us to find this end vector that is occurring here. So this end velocity vector as the ball hits the ground, as well as the angle at which it's doing so. So as always, let's start by drawing our vector diagram and labeling all the information that we have on it. Okay, so we have our two equations from part A for the horizontal velocity and the vertical velocity components, and we now need to resolve those together to find the resultant velocity at this particular point in time. So at the time when t is equal to 5 seconds. So the first thing we'll do is find the values for our horizontal and vertical velocity components at that time. The horizontal one is not going to change. It's a constant horizontal velocity of 20√3 meters per second, but the vertical velocity is changing with respect to time. So we need to substitute that time value of 5 seconds in to obtain the value of the vertical velocity at that point. And it is a velocity value, so we do need to list that it's a -30 meters per second. And now that we have those values that you can see I've transferred to the diagram, we can use Pythagoras' theorem to put them together and obtain that resultant velocity. And we can use tan to calculate the angle. And we finally finished the question.